Electroencephalography gives us a direct window into the brain's electrical activity, but decoding it is notoriously messy. The signal is low SNR, high-dimensional, and wildly non-stationary. To tackle this, the deep learning community has largely settled on a specific architectural pattern: separate one-dimensional convolutional layers for time and space. You process the temporal sequence, then mix the channels or vice versa. But what if you just combine them into a single two-dimensional spatiotemporal convolution? Mathematically, if there's no nonlinear activation between the two 1D passes, the operations are equivalent. So why do we keep them separate? And more importantly, does collapsing them into one 2D layer actually change how the network represents information? Or is it just a computational shortcut? Today, we're diving into a recent study that puts this exact question to the test, comparing sequential 1D convolutions against unified 2D spatiotemporal convolutions across shallow CNNs and transformer hybrid models. We'll look at the math, the training dynamics, and the surprisingly stark differences in representational geometry that emerge when you change just one layer. Let's start with the data structure. Raw EEG is fundamentally a multivariate time series. If you have C channels and T time points, your input tensor is shaped RCXT. The spatial dimension comes from the electrode montage, like the standard 1020 system, and the temporal dimension captures the continuous voltage fluctuations, usually sampled at 250 Hz or higher. Because T is typically much larger than C, the data is highly imbalanced across dimensions. The standard approach in models like EEGNet and ShallowFBCSPNet is to use two sequential 1D convolutions. For the temporal pass, you apply a kernel KT of shape 1 by m, sliding across the time axis. At each time step, it computes a weighted sum of neighboring time points. Then, for the spatial pass, you fix the temporal kernel size to 1, but expand the spatial dimension to match the number of channels. See, this effectively acts as a channel-wise dot product at every time step, mixing information across the scalp. Now here's the key insight from the paper. If you remove any activation function or normalization between these two 1D passes, the combined operation is mathematically identical to a single 2D convolution with a kernel of shape C by m. This 2D kernel slides across the time dimension while simultaneously applying a weighted sum across all channels in one matrix multiplication. So, in terms of raw representational capacity, they should be equivalent. But neural networks don't just compute functions, they learn optimization paths. The architecture imposes inductive biases that shape how gradients flow and how representations form. To isolate this effect, the researchers modified two state-of-the-art EEG architectures, a shallow CNN based on ShallowFBCSPNet, and a hybrid model inspired by the EEG conformer. Both normally start with those sequential 1D layers. The experimental variant replaces that initial block with a single 2D spatiotemporal convolution. Everything else remains identical. They evaluated these on two datasets from the BCI competition IV, processed through the MOABB benchmarking framework. Dataset 1 has 22 channels and a 4-class motor imagery task. Dataset 2 is simpler, with only 3 channels and a binary classification task. This difference in channel count is crucial, because it directly impacts the dimensionality of the spatial mixing operation. Both models were trained with 5-fold cross-validation, using the Atom optimizer, a learning rate of 1/10,000th, batch size of 128, and early stopping on validation loss. All training ran on a single V100 GPU, with full dataset caching to eliminate I/O bottlenecks. The first thing you'd expect to check is accuracy. And here, the results are almost suspiciously clean. The 1D and 2D models achieve virtually identical classification performance across both datasets. The variance across folds is minimal, which tells us the results are stable and not dependent on random weight initialization. But the real story emerges when you look at training and inference time. The 2D models train significantly faster, particularly on the 22-channel dataset. The per epoch duration drops noticeably because you've replaced 2 sequential matrix multiplications with 1. You're also reducing memory bandwidth overhead and kernel launch overhead, which compounds across layers. Interestingly, the 2D models sometimes require slightly more epochs to converge on the validation set, but the total wall clock time is still heavily in their favor. On the 3-channel dataset, the speedup is smaller but still present. This makes sense. When you have fewer channels, the spatial dimension is cheap to compute, so collapsing it into a 2D kernel doesn't save as much relative overhead. But as channel count scales, the 2D approach becomes a clear computational win. This isn't just about benchmark numbers. Faster training means you can run more ablations, test more hyperparameters, and reduce the environmental cost of training large models. For real-time brain-computer interfaces, faster inference is equally critical, since latency directly impacts user feedback loops. So if the speed and architecture change, are the models actually learning different things? To answer this, the researchers performed a band power reconstruction analysis. They took the activations after the convolutional block and ran a linear regression to predict the actual spectral power in 5 frequency bands between 8 and 32 Hz. The results show that both 1D and 2D models successfully recover these spectral features. The R-squared values vary by channel and frequency, which aligns with known neurophysiology. Certain electrodes and bands carry more motor imagery signal than others. But critically, there's no systematic difference between the 1D and 2D models. they're encoding the same spectral information. A correlational analysis of individual kernel activations against band power confirms this. The distributions of correlations are nearly identical across architectures, with slightly higher variance in the 3-channel dataset, simply because the signal from fewer channels gets distributed across more kernels. So at the feature level, the two approaches are functionally equivalent. But here's where it gets fascinating. When the researchers applied representational similarity analysis, or RSA, they found something that performance metrics and feature reconstruction completely missed. RSA compares the geometry of activation patterns across different samples. By flattening the activations after the pooling layer and computing pairwise distances, they built representational dissimilarity matrices for each model and fold. The matrices reveal a stark split. Folds of the same model type cluster tightly together, which is expected. But when you compare 1D models to 2D models, the dissimilarity spikes, especially in the 22-channel dataset. Even though both architectures learn the same spectral features and achieve the same accuracy, their internal representational geometries are fundamentally different. The 2D convolution imposes a different inductive bias on how spatial and temporal information is mixed and transformed. It's not just a mathematical shortcut, it's a different optimization trajectory that reshapes the latent space. This effect is much less pronounced in the 3-channel dataset, likely because the spatial mixing is so low-dimensional that the architectural choice doesn't have as much room to diverge. But in high-dimensional settings, the choice of encoding layer actively dictates the structure of the learned representations. This isn't just a theoretical quirk. It changes how we interpret model outputs. If you're using post-hoc interpretability methods to trace which features drive a model's decision, the architecture you choose will fundamentally alter what those features look like in the latent space. Two models can solve the exact same task with identical accuracy, yet their internal representations will map to cognitive states in completely different ways. This means that architectural choices aren't just about efficiency. They're a form of hypothesis about how the brain's signal should be structured before it reaches the classifier. The study also highlights a practical reality. Computational efficiency is often undervalued in deep learning literature. We treat training time as a fixed cost, but reducing it unlocks the ability to run rigorous statistical testing, explore broader hyperparameter spaces, and iterate faster. For BCI development, where data collection is expensive and real-time deployment is the goal, cutting down epic time without sacrificing performance is a genuine win. There are limitations, of course. The models were only tested on 2 motor imagery datasets with similar preprocessing pipelines. Bandpass filtering between 8 and 32 Hz was applied, and no baseline correction was used. Future work should test these architectures across different task types, sampling rates and channel counts, and systematically vary kernel sizes, layer depth, and optimizer settings. But as a baseline comparison, it's incredibly telling. So what's the takeaway? Replacing sequential 1D temporal and spatial convolutions with a single 2D spatiotemporal convolution doesn't change what EEG models learn at the feature level, and it doesn't hurt classification accuracy. But it does significantly accelerate training and inference, especially as channel count increases. More importantly, it fundamentally reshapes the representational geometry of the network, proving that even mathematically equivalent operations impose different inductive biases that steer learning down distinct paths. For anyone building EEG decoders, BCI systems, or working with complex multivariate signals, this is a clear signal to reconsider your initial encoding layer. Efficiency and interpretability aren't just trade-offs, they're architectural decisions that shape the entire learning process. If you're interested in diving into the paper, I've linked it in the description. Let me know in the comments whether you think architectural efficiency should be prioritized over representational consistency, and what other encoding strategies you've seen work for neural data. Thanks for watching, and I'll see you in the next one.